I'm going to talk about a little bit on the motivation behind developing Mantis2. So
let me go over there for you. Try that again.
There you go. Yeah, so the biggest motivation for developing Mantis2 actually comes from the fact that a lot of the modeling studies nowadays are based on plant-wide modeling, in which we are trying to model the liquid chains, which consist of activated sludge models, which can be modeled by activated sludge models. But then we have anaerobic digestions and some side stream processes as well. So when we try to apply the existing models, so the published models like ASM1, ASM2D, or ADM1, these models actually can't really be used very efficiently to model to construct plant-wide models. So that was one of the motivations to go for a comprehensive model which can do all these things for the modelers. Second thing which occurs basically is the development of new processes like ANAMMOX, which is a new process, and there is a lot of interest in modeling that process. And this process is not part of any of the published models. Also, to model ANAMMOX process, basically we need two-step nitrification, denitrification processes, which are also not part of the existing processes. In addition to the importance of these new processes, there is a great interest in resource recovery. For example, people want to model struvite and look into the precipitation of other compounds in these plants. So these processes are not built into published models. So these are some of the things which are lacking in the current models. Also, another motivation to go for a more comprehensive model, which is more complex, having more reactions built into the model, is that, well, we have come up with improved computational powers. So it's possible now to probably go for more complex models and solve them efficiently. Also, since the publication of ASM1, there has been improved acceptability of modeling approaches. So these are some of the motivations we had to go in and develop a new model, which is comprehensive model Mantis2. Just to highlight the importance of why plant-wide modeling, what is the importance of these kinds of comprehensive models. I'd like to show you two different approaches which can be used for plant-wide modeling. In approach one, we have a liquid train. This can be modeled by model 1, for example, activated sludge model number 1, activated sludge model number 2, or 2D, or any other variation of those models. But when we want to model the anaerobic digestion process, and we need a different model, which could be, for example, a model like ADM1. However, these two models have different set of state variables, and to connect these two models together, we need a state variable mapping interface to connect these two models. Also, when we want to go from model 2 back to the liquid train from the solid train, we need a state variable inverse map. So this kind of approach is a valid approach and has been used for quite some time, but it requires a lot of effort to have this state variable mapping and the state variable inverse map. As we can see that in this kind of models, the information of the state variables is lost from one model when we go to the other model. In approach 2, what we can do is we can use the comprehensive model in which we eliminate the need of state variable mapping between two models and have a comprehensive structure of the model which is valid for liquid train and the solid train as well. So this model essentially eliminates the need of state variable mapping and the inverse mapping, and is an efficient way of modeling, but it becomes computationally more, it becomes computationally more rigorous basically, and requires more computing power. But on the other hand, the merit of these comprehensive models lies in the fact that these are kind of easier to develop in the sense because you are developing one model which is valid for the whole system. So, so these are quite efficient for various purposes and to eliminate the need of mapping of state variables. So coming to the features of Mantis2 model, which we have implemented in GPSX right now. First of all, it models the carbon, nitrogen, and phosphorus removal in the process in the system. The model also takes care of anaerobic digestion reactions with gas-phase modeling for nitrogen, CO2, hydrogen, and CH4. It has built-in reactions for two-stage nitrifications using ammonia oxidizing bacteria and nitrite oxidizing bacteria. Also, we have included a methylotropic biomass because methanol, which is sometimes used for denitrification, can be consumed only by a specific group of bacteria. So we have a dedicated bacterial group for degrading methanol in the model. Also, we have included the ANAMMOX bacterial reactions in the model. The model also estimates the pH and alkalinity in both the liquid and the solid trains. Also, we have included the precipitation of different precipitates which commonly occur in wastewater processes. These precipitates are mostly the precipitates originating from calcium, magnesium ions, and sometimes if we are feeding aluminum and iron into the system, then those precipitates are also included in this model. Of course, we do the mass balancing in this system for COD, and we have extended the balance to include the carbon to model the pH in the systems, also nitrogen and phosphorus, and we have extended the balance to include calcium, magnesium, and potassium in the model. Also, the current model has 48 state variables, out of which 21 are soluble states and 27 are particulate states. These state variables are, if we compare them with activated sludge model number 1, for example, which has only 13 states, and ASM2D, which has 19 states, this is a large increase of state variables in this model. Also, this has 56 processes as compared to ASM1, which has only 8, and ASM2D, which has 21 processes. Also, an additional feature of this model as compared to the previous models which are implemented in GPSX is that we have a unified composite variable calculation which are based on global stoichiometry, which is defined for the model and is used throughout in all the unit processes. And just to describe how we went about developing this model, basically what we try to do is we try to review a lot of literature around different models which are available in the scientific publications, and we try to use the models, published models, and try to integrate those models to come up with a unified structure. So we took into consideration various models, for example, our two-step Mantis model, ASM2D model, and the model for anaerobic digestion is mostly coming from the University of Cape Town ADM1 model, which has been developed by Soderman et al., and with some modifications. And the inorganic precipitation model is mostly based on Matsumoto, and here also we have made some modifications for solving it efficiently. The models for ANAMMOX are coming from the published stoichiometry of the equation, and also the two-step nitrification and denitrification comes from various published literatures. So this is essentially to say that we have tried to consider the existing models which are out there and try to basically combine them in a unified way, because most of these models have been published in isolation and they uses different terminologies, different set of units. Some models are based on molar units rather than milligram per liter units. Some other models are based on carbon balance rather than COD balance. So we have tried to basically take care of the essential process information and try to convert that into a unified scheme to develop Mantis2. And this slide shows you the state variables which are there in this model. And the state variables here in the column of state variables, the state variables are shown in red. Those state variables are the new state variables which are introduced in this model as compared to the state variables which were there in ASM2D. So for example, as a new compound, we have introduced propionate into the model, methanol as an individual compound, dissolved hydrogen, dissolved methane, nitrite nitrogen, dissolved calcium, dissolved magnesium, potassium, cation, and anion. So these are some of the soluble state variables which we have introduced into the structure of this new model. When it comes to the particulate state variables, then we have new bacterial species. So earlier there was just one bacterial species for nitrification in ASM2D, but now we have ammonia oxidizers and nitrite oxidizers. Also we have ANAMMOX biomass, methylotropic biomass, fermentative biomass, and some of the other bacteria which are active under anaerobic conditions during anaerobic digestion. For example, acetogens, acetate, methanogens, hydrogen methanogens. So those bacterial species have been included into the model. Also, we have included some other pest states which are commonly found in wastewater treatment plants, like calcium carbonate, calcium phosphate, magnesium hydrogen phosphate, magnesium carbonate, and fluoride.
Okay, sorry about this mess up there. So now we are going to just go over this slide one more time, and I was just trying to explain what happens when for the processes which are involved with heterotrophic organisms. So this is a very similar flow scheme which we have in ASM2D, in which there is a fermentable COD in which heterotrophic biomass decays and produce slowly biodegradable substrate, and which is hydrolyzed and gives rise to fermentable COD. So in ASM2D we have two substrates which are used by heterotrophic biomass, like fermentable COD and acetate. In addition to this, in this particular model we have introduced another compound which is propionate, and heterotrophic biomass can use propionate for biomass growth as well. So also, in addition to oxygen, like under aerobic condition, this is the pathway. But when we have anoxic conditions, in the anoxic condition in ASM2D, nitrate is directly converted into nitrogen gas. But in this particular model, we have included nitrite as a electron acceptor as well. And in this process scheme, nitrate is converted into nitrite, and nitrite is converted into nitrogen gas. So under aerobic and anoxic conditions, we had to declare new processes in this model. Similarly, here we had to make modifications in the model to include the reactions which are mediated by ammonia oxidizers and nitrite oxidizers. So in this particular scheme, there is a decay of several biomasses which are there in the model. The decay produces particulate biodegradable nitrogen, which is hydrolyzed to soluble organic nitrogen, and which is converted to ammonia by the process of ammonification. And ammonia is used by ammonia oxidizers and using oxygen, and it's converted into nitrite. And nitrite is again used by nitrite oxidizers for growth, and using oxygen it's converted into nitrate. So these are some of the modifications which we had to do in ASM2D to include the biological reactions conducted by ammonia oxidizers and nitrite oxidizers.
No, I think we're good.
This is the scheme actually for biological transformations which are conducted by poly-P, the phosphorus accumulating organisms. And in this particular case, we have the processes under anaerobic and aerobic conditions in which acetate, for example, is taken up and converted into PHA. And in this particular process, the polyphosphates produce orthophosphates. Also under anaerobic conditions, the reverse process happens. The orthophosphates are converted into polyphosphate and they consume PHAs, and oxygen is utilized. So this is a very similar scheme which is there in activated sludge model number 2D. And in this particular case, what we had to make one more modifications, which is add another compound which is propionate. And it is well established that poly-P bacteria can also consume propionate and convert that into PHA. So another process was added into the model which which models the uptake of propionate for PHA accumulation. And the anaerobic digestion processes which are basically used in the model are based on UCT ADM1 model, which I mentioned before. So in this particular model, this is a little bit of a simplification of the anaerobic digestion model number 1. And in this, the simplification comes from the fact that the slowly biodegradable substrate is not really divided into proteins, carbohydrate, and lipids, but it's considered as a composite slowly biodegradable substrate, which is hydrolyzed, which produce fermentable COD, and then it is used up by different bacterial groups. It's used up by different bacterial groups to produce propionate, acetate, and hydrogen, and which are further used by two bacterial groups like acetoclastic methanogens and hydrogenotrophic methanogens to produce methane. So this is the overall scheme which is produced, which is given for this model from which is called the UCT ADM1. And in this one, just to make it complete, we added new processes which are heterotrophic biomass, nitrifier biomass, and power biomass, which decay and produce slowly biodegradable. Sorry, this should have been the slowly biodegradable substrate. So this produce slowly biodegradable substrate, and the hydrolysis process produce fermentable COD. So these are some of the modifications which we had to go through. This is not the complete structure, but this kind of describes the essential details of how we use different model structures to combine together and try to come up with a unified structure for Mantis2. For ANAMMOX, the typical reaction for ANAMMOX is ammonia nitrogen and nitrite nitrogen basically react together to produce nitrogen gas and a little bit of nitrite. So this reaction is incorporated in the nitrix for Mantis2. Coming to the chemical processes, we have weak acid and base equilibrium reactions, which incorporates different species like carbonic acid speciation, phosphoric acid speciation. We have ammonium ion speciation, acetic acid, propionic acid, and HNO2. So speciation of all this compound is calculated based on equilibrium reactions, and based on which we try to develop a charge balance equation, which is an algebraic equation, and try to solve for pH in the model. For the chemical reactions, chemical processes, as I already mentioned, there are 7 precipitates which we include in the model. So I won't go into each one of these, but there are 7 precipitates which are the main ones in the wastewater treatment plants. Also, we model the gas liquid transfer as a physical processes. We model the gas liquid transfer of CO2. Gas liquid transfer of nitrogen gas, CH4, and hydrogen gas. So we use the two-film theory, the gas liquid phase transfer across a liquid and the gas film, and we model it by reaction rate using concentration difference and the mass transfer rate constant. And to estimate the concentration of CO2 in liquid, we use the speciation, which is estimated based on the equilibrium reactions, and from there we estimate the liquid concentration, the CO2 concentration in the liquid phase, which is kind of gets equilibrated with the gas phase. And similar expressions are used for gas transfer required for nitrogen. Well, we don't have ammonia right now, but we have nitrogen, methane, hydrogen, and oxygen. And this is a very an attempt to show all the mass flows going into the model, but we couldn't really complete this. This is just a partial thing and shows that there is a mass flow happening all across the model between different states. So if we try to put a complete model thing here, it will become very complicated. But it shows the mass balance from how the mass is flowing between different states in the model. Also, in additional considerations, we had to extend the biomass structure to include the balance for calcium and potassium. Also, we now model the polyphosphate composition in which we account for potassium which is taken up by the polyphosphate. Also, we include the different yield factors for aerobic and anoxic growth. We have different yield factors for different substrates. For example, methanol, the yield on methanol is much lower than other substrate. Also, we apply appropriate reduction factors for two-step nitrification. This is just to keep the fact that our reactions are not way too high just because we have divided them into two. Also, as I said before, we have now uniform composite variable calculations in the model. So once we define the global stoichiometry of different state variables, then the composite variables can be calculated for each unit process without defining them separately for the processes. So we made the first release in GPSX 6, which was in 2011, and what we did, we implemented this model in GPSX. In addition to implementing the model, we had to develop an influent object model so that the influent can be characterized easily. Also, we added some new objects, which are the acid objects like acid feed objects, alkali feed objects, COD feed, and nutrient dosing objects. So with this model, it's possible to estimate the consumption of acids, consumption of alkali for pH adjustment in the system. Also, we did a lot of model testing. The first testing, of course, the mass balance testing, and then the model calibration using our in-house test layouts. We did a lot of calibration studies, also collected different information from different literature sources and tried to see that the model outputs are valid and they are in the reasonable range of the reported values in literatures. And we made some adjustments to the model parameters as well. And in 6.1, actually, we have provided some more information or quite a lot of details about Mantis2 model. So for your further interest, if you go back to the manual, you can read more about Mantis2 model in the reference. We have come up with a new update in 6.1 in 2000.
The first one was in 2010.
Sorry. So
and then the newest in 2011. Yep.
Okay. And in the 2011, what we did, we added a new UASP and EGSP reactor model in Mantis2. And also we have added a new sludge pretreatment reactor to model the thermal lysis or ozonation reactions and those kind of things to disintegrate the sludge and make it more amiable for degradation in anaerobic digestion or activate sludge treatment systems. So these are some new models. Also, we noticed that once we develop this model, there are some processes which are not necessarily important for all the modeling studies. So we developed an option for user to switch on and off these reactions depending on the need. So for example, if precipitation reactions are not of much importance in the layout, then it's possible to switch them off and calculate the system. Make the calculations faster or easier, basically, without getting worried about the precipitation reactions. Or similarly, that's true with any other reactions. For example, if you're not adding methanol, you can turn off the methanol degradation reaction. This is some of the experience we have got here. We have got some of excellent feedback from our clients who have spent time to learn the model and applied it for some of their studies. We've got some good feedback from them. Also, we are using this model for our in-house projects, and we have had very good success in using this model. And some of the future targets, actually, we are we are trying to continuously improve the model and trying to incorporate whatever is the latest information coming out from scientific community. And also we are in the process of incorporating some other enhancement to the models, like for example modeling N2O production model, the pH dependent kinetics, and nitrate. Nitrogen is a source for nitrogen for growth, temperature modeling, and some of the list which we have for further improvements. Also, we are committed to develop new unit processes. For example, we did last year USB process. So in the coming versions, we are trying to look into some other processes which we can include in the new release. And with this, I would like to just give you a small demonstration.
Yep.
So this is how it looks basically, and if you look at the center here on the toolbar here, you can select between different libraries, and at the bottom you will see the comprehensive carbon, nitrogen, phosphorus, pH, Mantis2 lib. So to use the Mantis2 model, you have to be in this comprehensive library. And on the left-hand side, you can see here there are some additional objects which are acid doses object, alkali doses object, nutrient dosing objects. So these are additional objects which we have provided in this library. These objects are not available in other libraries. Also, if we go for attached those systems here, we have the USB object here. And in the sludge biosolid treatment, if we go, we have the sludge pretreatment object here. So we have some new objects here which are not available in other libraries. So when you are in this library, if you go to, you can build your layout as similar to as you do in other libraries. But in this library, you will see that if you click on the biological reactor, you will just see one model, which is the Mantis2 model. So this is the one model which is applicable for all the processes, for aeration tank, for example. And if you go for anaerobic digester, you can see the model my Mantis2 here too. So it's the same model which is applicable for the whole plant. And if you just look at the influent characterization here, you will see that it's much more elaborate now. There are more state variables and more state variables which needs to be calculated, and we have provided more information with respect to different composite variables. For example, now you can estimate the soluble organic carbon, which is, or the total organic carbon TOC in the reactors. You can do that. And also with respect to the other ions, basically it requires more information about, if you have the information for other ions, like for example the calcium, magnesium, potassium, you have to enter all that information here. Also in the influent object, we have environmental settings where you can set the pH of the influent, and once you set the pH of the influent, the model automatically adjusts the cations and anions concentration so as to give you the pH which is set here. If you don't want to do that, then you can say estimate the pH, and based on whatever concentrations you have specified for your state variables, the model is going to calculate your pH for the system. So I'm going to just run this model and just show you how this is quite easy to run and give you all the information which you need through just one model here. So this solves the model, and then you can see the information about different unit processes here. For example, in the activated sludge tank, you can see all the information about MLSS, MLVSS, and pH in the system. Since there is nitrification, you can see the pH is dropping. Also, you can see some other process variables here. Also, for example, if we go and click on the anaerobic digester, we can see the information for this process here. For example, the VSS coming in VSS concentration is 33,000, going out is 12,000. So VSS destruction rate of 65%, with a gas flow rate of 2200, and the methane content and the CO2 content. So all this information can be generated from this model. Also, this is some additional graphs which you can generate to see the profiles along the aeration tank here. So so this is basically all what I wanted to describe today.
Thank you for watching this video. If you're interested in information on our other software products, such as CapDebtWorks for preliminary design and costing, ToxChem for industrial wastewater treatment modeling, or WattPro for drinking water treatment modeling, you can visit our website at www.hydromantis.com for further information.